Welcome all. So in the last session we discussed about the work done in deforming a body in the case of longitudinal strain. So today we will discuss what will happen in the case of volume strain. So already you studied when we apply some force or some stresses applied to some material, there will be some changes in linear or longitudinal changes or volumetric volume changes, or there is some change in shear. So now we discuss what will be the work done when there is some volume changes or volume strain is happening. So first of all, consider a body of volume V. So this volume will be the original volume of the body. So I just give the letter capital V, and when we apply some force or some pressure on that body, it will compressed by an amount, or there will be some changes. Okay, so I here take it as a compression, so compressed by an amount. V, small v. Okay, so this letter denotes the compression of that body. So compressed by an amount V by the application of uniform pressure. So the pressure will be denoted by capital P, acting normal to the surface, acting normal to its wall surface. Okay, so now we will write the equation for rigidity bulk modulus. So bulk modulus will be, already you know, the modulus of elasticity. The constant will be obtained by taking the ratio of stress and strain. So here bulk modulus will get by taking the ratio of stress, that is here in the pressure P, and with respect to the strain. So strain will be small v divided by capital V, and we will get it as capital V divided by small v, and the bulk modulus will represent by the term capital K. Okay, so from this equation we will get P will be equal to K small v divided by capital V. So this is equation number 1, and this one equation number 2. So if the surface area of the body be A, so then the compressive force acting on the body can be written as, so you already know what is pressure. Pressure will be some force acting on the particular area. Okay, so if the area is A and the force is acting on the body will be the compressive force acting on the body can be written as body is F equal to PA. Okay, this equation you got from P equal to okay, I just written here P equal to F by A. So F equal to PA, and this substitute the value for P, you will get K small v divided by capital V into A. So this is equation number 3. So now we will consider a small amount of work done for a small movement of dx. Okay, the small amount of work done for a movement dx in the direction of F is given by, that is normal to the surface. Okay, that is normal to the surface and is given by dw, that will be the small work done, will depend on the force into the into small displacement we will consider. So F into D, that will be, so F into dx. Okay, so F is already, you know, what is that, K small v divided by capital V into A dx. This is the equation. And you already know area into displacement will be, there is area into displacement, A into D will be the volume. So therefore A dx will be dV. Okay, and we will give that value here. So we can write it as K small v capital V dV, that will be dW. So this is equation number 4. Now we will find out the total work done for a change of volume V. So therefore total work done for a change of volume small v. So that we will obtain by taking the integration of equation 4. W will be by integrating dw, and we will take the limit will as 0 to v. Okay, so 0 to v k v divided by capital V dV. Here k by v as the constant value, so you can take it outside, and we will get k by v, and v dv will be the, in integrating v dv we will get v square by 2, and applying limit we already get it as v square by 2. Okay, this is the value, and we can write w equal to half, and take this half to outside, and k v, split this v square into v into v, k v v divided by capital V, and this is 1, and small v. So this will be equal to half into k v v by v will be pressure and small v. Okay, so this equation will be half into pressure into change in volume. Okay, so hence the work done per unit volume will be unit volume is W by V equal to half into kV divided by V into V divided by V. This is the equation, and we can write it as half. This term will be the stress. Okay, stress into, and this one will be strain. So we got the work done per unit volume will be half into stress into strain. So this is the final equation. This equation also already we got in longitudinal strain also. So work done per unit volume will be half into stress into strain. Now we will discuss what is the work done in the case of shearing strain. So let us consider a cube I will just draw the cube here. So consider a cube. So consider a cube here, and I am applying some force on the upper side. So what will happen? It will tilt to some other position. Okay, so I just draw that tilting portion only here. So this is the portion I drawn here. So I will now write the phases of this cube. The green cube is the original cube one, and here it will be A, B, C and D. Okay, so the phase A, B, C, D you can see here, and when we apply some force on the upper side, it will move to, or there is some tilting happening on the upper side only. So A will be changed to A dash and B will be changed to B dash. Okay, so by creating an angle theta here. Okay, this is what we'll see on the shearing strain. So now we can write the modulus of rigidity. Okay, so the rigidity modulus will be obtained by rigidity modulus will represent by the term n, can be obtained by taking the ratio of stress and strain here. So here the stress will be force by area and divided by strain. Strain here happening here is the shearing strain that we can represent with the term theta. So F by A theta. Theta can be represented in terms of longitudinal strain. So we already derived the value of theta here, theta already. So where theta will be change in length by original length. So we can give this substitute this value on equation 1, and n will be equal to F by A L small n. So this is equation number 2, and from this equation I will find out the equation for force. Okay, so force will be N A L divided by L. This is the equation. Then the work done during a small displacement here we will consider dl. Okay, displacement dl is dw equal to F into dl. So F is N into A L divided by L into dl. So this is the equation. Now we will find out the total work done for the displacement from 0 to L is W equal to integration of dw with the limit 0 to L dw, and we will write integral 0 to L F into dl, and it will be 0 to L N A L divided by capital L into dl, where N A by L all these are constants, so we can take it outside. NA divided by L, and LdL, by integrating LdL you will get it as L square by 2 and applying the limits. So now we will write W equal to, half will be taken outside, N A L, L will be split into L into L, NaL divided by L, this is the one term, into L, and this will be equal to half into, this term will be F half into L, okay, Fi. So half into tangential force into displacement. This is the another equation for work done, and now we will find out work done per unit volume. So work done per unit volume will be W by V, and it will be equal to half into F L divided by V. Okay, so let's do some arrangements here. That V will be, by writing F L, V is A into L, area into length. Okay, so sorry, area into original length. V is the original volume, so A into capital L. So we can write it as F divided by A, L divided by L, and here you can write half into F by A is stress, and L by L will be the strain. So here also we got work done per unit volume is half into stress into strain. So on all cases the work done will be work done per unit volume is the value half into stress into strain in the three cases. Okay, so let us now discuss some problems. So problem 1. So calculate the work done in stretching a wire of cross section 1 millimeter square and length 2 meter through 0.1 millimeter. Young's modulus of the material of the material of the wire is 2 into 10 raised to 11 Newton per meter square. So here you have to calculate the work done in stretching a wire. Okay, so already we know the equation for finding the work done. So I will first write the terms that's given here. The value for original length is given here 2 meter, and the area is given as 1 millimeter square, so that we can write in terms of meter square. So it will be 10 raised to minus 6 meter square, and next the change in length is given, that is small l, that will be 0.1 millimeter. That also write in terms of meter, so it will be 10 raised to minus 4 meter. And y is given here, y will be 2 into 10 to the power 11 Newton per meter square. And work done is half into stress into strain. And here half, work done will be half into stress into strain into volume. Okay, and it will here stress can be obtained from y L by L. So y L by L will be the force, okay, and strain will be L by L itself, and the volume will be A into L. So this is the equation. So stress will be y L into L, that will be from the equation from the Young's modulus, that is stress by strain. So stress will be y L by L, and L by L will work for the strain, and volume will be A into L. So from this equation you can write half, 1L will be cancelled out, so y L square area divided by capital L. This is the equation, and substitute for these values here. Half into y will be 2 into 10 to the power 11, L will be 10 raised to minus 4 whole square into area will be 10 raised to minus 6 divided by L will be 2 meter, so 2, then you will get the value will be 5 into 10 raised to minus 4 joule. So this is the value for work done. Thank you.